let's do the consensus for the friction lab. And here's what I expect to see in your notebook when I grade it. You have your data table, and then after you have your data, you should graph your data. You should have your force of friction in newtons as a function of normal force in newtons. And it should come pretty close to a straight line. So draw your best fit straight line through your data, and then come up with your mathematical model. A force of friction as a function of the normal force, and here we go. Now, let's take a look at this. This is kind of interesting. Groups 1, 2, 3, and 4, there's some consistency. There's actually a little consistent mistake in groups 1, 2, 3, and 4. Do you see what it is? Let's take a look at the slope here. You all have about the same slope, 0.3, 0.4, 0.35, 0.34, which is good, very consistent results. But this is measured in newtons, right? And this is measured in newtons. So when you do the rise over the run, you have blank newtons over blank newtons to get your slope. And what is well, you could write it like this. 0.4, the slope would be in newtons per newton, right? And there's nothing wrong with that because it is 0.4 newtons per newton. You get 0.4 newtons of friction for every newton of normal force. Does that make sense? 0.4 newtons of friction for every newton of normal force. Now that should be what your conclusion is. Because you need to answer the question, how does the force of friction depend on the normal force? Well, if you're group 1, you would say we get 0.4 newtons of friction for every 1 newton of normal force that we add. And it's directly proportional. Okay. So these all, now if you have a newton per newton, that's the same thing as having a nothing. So you shouldn't have newtons on here. You should just have 0.3, or you either have to have newtons per newton, or you have to have nothing. Now let's take a look at this. This is the people who did the static friction experiment. 0.4, 0.3, 0.45, 0.34. If I were to average that, what would it be close to? Well, I'm going to say the force of static friction is approximately equal to 0.35 times the normal force. Is that about right? That's a nice, like in the middle of what everybody got. Now let's take a look at this kinetic friction. Very consistent results. 2.6, 2.6, 2.5, 2.5, 2.7. So I'm going to say the force of kinetic friction was 0.26 newtons of friction for every newton of normal force. That's beautiful. This is what I was hoping to see, and we saw it. So, now, you don't have to copy down all these mathematical models, but go ahead and copy down these results, because we're doing consensus right now. So our class got 0.35, force of friction was equal to 0.35 times the normal force, and for kinetic friction we got 0.26 times the normal force. Now this ratio, this slope, okay, so if you graph force of friction as a function of normal force, you're going to get your data will line up pretty good, and you get a straight line. Now the slope of this, that is how much friction changes for every quantity of normal force changing, we have a name for this ratio. It's what fraction friction is going to be of the normal force. And as you saw, it works pretty good. I mean, this is a pretty straight line. I saw some of your graphs, they were perfectly straight. This ratio is called the coefficient of friction. It's a measure of how slippery something is. The lower the coefficient of friction, the slipperier it is, the less friction you have. Whereas if you have a high coefficient of friction, you've got a lot more. You get a lot more friction. It's like grippier, like steel on ice would have a very low coefficient of friction, like 0.1 newtons of friction for every newton of normal force. But like pavement and the tire rubber on pavement, dry pavement, it's going to be very high, like 0.8, 0.9, 90%. Okay, now we have a symbol, and by the way, if you're leaving for CART, could you just leave very quietly because I am recording this. We have a symbol for this, a variable that we use to represent the coefficient of friction. It's mu. This is a Greek letter mu. Here's how you remember how to say it. It's pronounced mu. Okay, now American cats, in America, cats say meow. But in France, cats say mew. It's true. You'll remember that. It'll help you remember. Mu. So we can say that the force of friction is equal to mu times the normal force. Okay? Now we have two kinds of friction. We have static friction, so you need a static static coefficient of friction. And really, this is the maximum possible. So I'm going to do this. The force of static friction, this is a maximum. The maximum possible for static force of friction you get will be equal to the static coefficient of friction for those two materials times the normal force. Now this is called a coefficient because it is a dimensionless number that just multiplies. Now what did we get? We got our force of static friction was 0.35 times the normal force. So this was the coefficient of static friction between your tabletop and the paper that the envelope that you slid the weights across. Now we have a force of kinetic friction. So we have a kinetic. That is, the two surfaces are sliding with respect to each other. And so for the experiment that we did, it was about 0.26 times the normal force. Okay? And notice that the coefficient of static friction is almost always greater than the coefficient of kinetic friction for a given material. That's why I was really happy to see the data you got, because it really agreed with that. So now we have an equation. Well, mu is defined to be the force of friction divided by the normal force, and you can have static or kinetic right here as your subscript. So this is an equation that we can use to add to our equation list. We also say, hey, the force of friction is equal to mu times the normal force. So, I mean, these are the same equation, right? We just rearranged a little bit. Now, how do you use this? Well, now, when you have your crate and you're sliding it across the floor, here's a crate and we've got some, it's got some mass, and we've got some pulling force to the right, but it's got friction. So when I draw the free body diagram for this, okay, we got mg, that's the force of gravity pulling it down. We've got the normal force pulling it up. You got this pulling force, and you've got this force of friction. Now let's say we're dealing with kinetic friction. Let's say we're moving this with some velocity. Well, now I can sum the forces in the x direction equals ma in the x direction. Let's make this x and y. Well, now I got this pulling force minus the force of friction equals ma. But now if I sum the forces in the y direction, I'm going to get 0 in this case. And I'm going to have the normal force minus the weight equals 0. Well, this tells me that the normal force is equal to the weight. And now I can use that, I can use this to say that the force of friction is equal to mu times the normal force, but this is mu, the normal force is equal to the weight, mu mg. So now I can substitute this in here and solve for the acceleration or solve for the pulling force. Last thing. In your book, and if I can find my book,
Up here.
Where is it? Can you bring it here?
Yeah.
Thank you. Well, go faster. I know you're in pain.
Sorry.
Jod worked out. He's in pain.
He ran a mile.
It's in chapter 4. If you look in here, look on page 90 of your book, and there's a table. And they might give you problems where they tell you what materials you're dealing with, and you have this table. And look, you have like wood on wood, metal on metal, rubber on dry concrete, Teflon on Teflon and air, and you have different, here's the coefficient of static friction. So if you need that maximum static friction, you can look it up here, or here you have the coefficient of kinetic friction. So you can look up those coefficients of friction. Usually on the test or whatever, I'll give you the coefficient of friction, or you'll be solving for it, okay? So, let's zoom out. Any questions? That is all.